The next speaker is Pierre-Louis Théron, who's going to speak about something entirely different, peer-to-peer.
Hello everyone, I am Pierre-Louis, I am the CEO and one of the founders at Streamroot, and I'm going to talk a little bit about another way of seeing the delivery, which is kind of the extension of the CDN architecture that we are all used to by leveraging the device and the client side of the delivery. We've been working for the past few years on measuring and acting directly in the device to make sure that not only we can do some really interesting things on the CDN side to optimize the architecture, but we can use the device as a key piece of the CDN architecture. So we're going to talk about peer-to-peer, yes, and also client-side load balancing. For those who don't know us, basically we are providing a handful of services. The first one, which is peer-to-peer WebRTC-based streaming technology. The second piece, which can actually work in combination with the first product, is client-side midstream switching multi-CDN technology. So basically making decision on the client to switch between different CDN sources. And third kind of a product we've been working on also on the peer-to-peer side, but really more focused on complex ISP environment or behind the firewall use cases for enterprise CDN streaming for corporate communications. So we've been delivering a handful of events. We been working on large-scale broadcast, live linear video delivery, but also on demand. So we have been able to use all this data from more than 20 million unique peer sessions per day. And this data basically helping us to understand what's really going on in the device and how we can act to make that really successful. Before we dig into the data, and I show a bunch of different like A/B testing and client-side analysis we made, just want to take a step back and perhaps do some education. Perhaps some of this would be super simple and trivial for most of you, but I'd like to make some education on WebRTC because that's becoming a more and more interesting topic used for different kind of use cases, and I want to make just a difference between like what WebRTC can be used for. First, it makes a difference to use it for client-side delivery. What is really interesting about this approach is that obviously you're creating micro-caching. You can do intelligent assembling of the segments on the client side, and WebRTC has a handful of really cool features. First, it is completely transparent for end users. So you can use it for either peer-to-peer or low latency without having to ask the user to do anything. Second, it's leveraging a handful of open source library that has been produced and supported by most of the big players in the market. It is widely adopted. There's been a big problem for a long time, but even Edge and Microsoft are going to be supporting the whole stack of WebRTC pretty soon. So the entire browser base is going to be supporting WebRTC, and today it's 95%, I would say. Native devices, iOS, Android, obviously, but also set-top boxes. You can run WebRTC on a very large scope of devices. It's great for low latency communications, which can be used for different use cases. Low latency is great for one-on-one communication when you're doing Skype-like use cases. It's great when you want to go to a low latency broadcast for sports or gambling. And it's also great for doing some peer-to-peer exchanges because you have a very, very efficient way of sharing segments and packets between users. And there's a lot of security already baked into it, which doesn't make it a big black box. Last point on WebRTC before we dig into more the specifics of the client-side optimization we're doing is, again, clarification between three main APIs that you will find in WebRTC. The first one, on the top right of the screen, it's what is called Get User Media. And basically, this API is primarily used for the Skype one-on-one communication use case, where you need to have access from a browser or from a device to the camera and the microphone of the device. The two other ones, this is what's going to be interesting for all of us here. The first one, the one in the middle, which is RTC peer connection. Again, this is a simplified view, but this is basically what you're going to be using to do a WebRTC stream. So you can use that for one-on-one communication, creating low latency WebRTC stream for one-on-one communication. And since we've seen over the past 2 years more and more use cases and vendors that are working on doing low latency streaming using this RTC peer connection. And there's a last bucket of APIs which is named RTC data channel. And this is the piece that we are exploring the most, which is basically opening a data channel between any device where you can send any kind of packets. That can be packets for video, that can be packets for a file, whatever it is, but you can create a connection and send packets between users, which is, you understood it, very useful to do peer-to-peer communication. So just to clarify, when you think about WebRTC, it can be 2 or 3 or even 4 very different use cases. So now just to why we believe that the client-side optimization is very important. First, there's a lot of things that's moving and changing in the client. You can have CDN changes. You can have a problem on the connection with your CDN and this specific ISP. You can have a second software that is running in the same device that's going to use most of the CPU or of the memory. So there's a lot of things going on in the device that can have impact on the user experience. And obviously, measuring that in real time enables you to have a dynamic behavior. The most basic and most popular application and example of that all of you know about is the ABR. So players using ABR by measuring what's going on in the specific device to change and move between the different bit rates. But we believe that there's more you can do than just changing bit rates. We believe that what if the solution is to switch dynamically from one segment to another to a different CDN? Or what if the solution is just finding another source, which can be a peer-to-peer source? So not only just changing and going down in bit rates. Being in the device also enables you to go faster. You can do faster reaction. You don't have to ping back a server-side intelligence that's going to measuring what's going on the network to make decision. You can act right away in the device because of what you've been measuring. So it's dynamic, and you can go faster. One example too, when you have to go back, and most of the CDN switching right now are leveraging backend kind of DNS switching, and that's introducing less reactivity than just acting right away in a device. And obviously, you can make decisions on a more granular basis because 2 different users might have different conditions, and you might not want to do the exact same changes or optimization between these 2 different users. So we, in the player, in the device, there's a lot of data that you can use properly, if used properly, can really improve the overall user experience and optimize the CDN architecture. So now, how we are doing that? So first, again, there's already a handful of complex logic that are present in the player. I mentioned ABR for most of the player. There's also logic like when you abandon these segments, the download of a segment to switch to another segment's quality, or having different backup URLs that's going to be available in the player so you can switch between these different URLs. But we definitely take it a step further. What we are doing to optimize our algorithms, both for the peer-to-peer delivery or the CDN switching, is looking at the use cases. Are we on the live or VOD use cases? What's the streaming formats? Depending on the streaming formats, depending on the length of the segments, depending on the bitrate profiles, you might not want to have the same exact logic of segments download inside the player, inside the clients. Obviously, we're going to also look at all the QoS metrics that what everyone is measuring, looking at the metrics like the buffer, obviously, the buffer hairs, the bitrate, the track switches, the drop frames, all of that can give you information, not only to look if one CDN is good or not, but perhaps to act immediately there. There's some, obviously, information, networking information that you want to look at it on both the throughputs and the error rates for the different sources that you have. And also looking at what's going on in the device, like the RAM, the CPU, the battery level. Again, all of that should have an influence. It's very good information to have to make sure that you make a decision by really knowing what's going on the device. So quick of explanation on the approach. So basically here you have a user, a video player, watching a content connected to a handful of different sources. And in these sources, you have the CDN sources, and you have also the other users that might be watching the same content or the same stream. The logic that you can implement in the player is basically intercepting the request from the player that's usually going to go to one given CDN and try to find if this request is going to go to the origin, the CDN, or the different peers. So that's the video segments that you're going to see here. That in that case, for example, you're going to fill a video segment, an HLS or a dash segment from different peer-to-peer sources. So that's one use case that can happen if the client side has been deciding that they are the best sources available. That can be going back to one CDN if we believe that the performance is better on CDN B. If when you download the second segment from CDN B, you see that you have an error. The cool thing about being in the client is that you can switch without having any interruption in the stream. Once the next segment is coming, you've been measuring there's a problem on either the peers or the CDN you are supposed to go after, and you're measuring that, and the next segment you can get it from another CDN and another source. So here you just go to CDN C on the next segments without breaking the stream and having to start again to find another CDN. And that can be a bit of everything. That's the cool part. You can get some pieces from the peer network, some pieces from the different CDN by doing byte range requests, and even doing that at a sub-segment level and not switching and not doing this logic at a segment level. So I'm going to give you a few examples of how by doing a lot of A/B testing with the data, you can actually iterate use this data to make sure that you're improving the client-side algorithm. And I'm going to take two examples. The first one is an example on the iteration of the number of peer connection that a given user should have. And the second is an example around some metrics around the upload impact, depending on the users. One user might be uploading much more than another user, for example, in a peer-to-peer use case. So basically, the key goal there when you're increasing the number of WebRTC connection on the client is to make sure that you're not having an overusage of the CPU of the machine. Because if you're opening 1,000 WebRTC connection, you can imagine that the device might have some trouble handling all of that. So obviously, you want to, at the same time, maximizing the number of connections without having any impact in the device. So back in the days, we had like a kind of a conservative approach by limiting the number of peers the maximum number of peer connections that you could have on the client. And at one point to say, hey, why don't we make this behavior much more dynamic by measuring what's going on in the device. So what you see here is the experiments of the A/B testing. With people on our team has been spending quite a lot of time being able to gather all this data and be also able to analyze properly this data, because sometimes you can find some counterintuitive things if you don't do things properly. So what you see here is the distribution of number of peers connection. So here you have at the top left only users that have 0 peer connection, and at the top right, I think it goes up to 30 WebRTC connection open. Before, the distribution were capped at 15. So that's why you see in blue, that's the blue, it's the previous distribution before we implemented any dynamic behavior. So you see that it's capped at 15. You have a pretty big number of users that have 15 connection open, and then you have a bunch of them that have 0, and you have the distribution like that. After we did the dynamic behavior, you see that you have a much more distributed audience between the number of peer connections. So you see that there are actually a pretty significant amount of users that could open much more connection without having any impact on their CPU. And you see that there's a much more smooth distribution. So really, looking at what's going on in the device can help you make smart decisions on lots of your algorithm. Not only we've seen a better distribution of the peer connection, but they did have impact on the buffering ratio, so less bufferings with the population that had the dynamic behavior compared to the one that had the fixed behavior, better peer-to-peer exchanges, and a better, less dropped frame in that population too. The second example is around the effect of the upload on the QoS. So really the idea is to analyze, okay, what's the impact of a user that is uploading much more than a user that is not uploading at all? Is the QoS actually the same? Is it better for one? Or is it worse for another? And the really interesting thing, again, in this graphic, you see a distribution of the users between the users that on the top left are doing 0% offload, so they upload, sorry, so they don't upload anything. And on the top right, users that are doing between 90 and 100% upload. So they are actually uploading almost as much as what they receive, okay? So this is kind of a distribution, and in red, you see that's actually the buffering ratio for this user. So if you look at that, you see that actually there's, if you do things properly, so you actually only use the upload of the users that can do it and have enough resource in either bandwidth, resource, CPU, and capacity, you won't have a negative impact for the users that do the most upload. And in that case, it's actually, I mean, it's almost the same, but it's even a little bit lower for the users that are doing more upload. They have less buffering. It's also because they probably have a better connectivity connection, but it means that we are really good at, I mean, it's really easy to find the users, to tell the user what to do when you do it dynamically. A few more examples here that I'm gonna talk about right now. So here is again some A/B testing numbers that we've been doing by users that are basically comparing population of users that's only doing CDN and population that are leveraging client-side decision-making with peer-to-peer and multi-CDN switcher. And you see that comparing this population between, depending on the countries, depending on the use case, here we listed a few countries from our customer. You see some 15% improvement on the buffering ratio, 30% improvement in some countries, 6% improvement in others. So this is really what you want to look for by leveraging the device. Is like, at the end, it should be better than just a CDN. And why it's better, I mean, I explained it earlier, is because you have more decision to make and not only one sources. Another interesting graphic here is to see the correlation between buffering ratio and users, and number of users that are watching the stream. So here again, on the left is the buffering ratio, and on the top is the number of users that are actually joining the stream. And one of the big problems that everyone is trying to solve here is the scaling for big events. And usually when you scale and you have a very, very big spike, this is where you're afraid that you're going to have more buffering, because there's a chance that some of the CDN that you're using are actually saturated, or there's some peering. Even if the CDN is not saturated, there might be a peering point between the CDN and the ISP that it is. By keeping traffic locally and doing some switching between the CDN, we see that actually the more users you have, the more sources you have, so the lower is the buffering. And you see the same thing here by looking at the metrics again. The blue is the number of users watching a stream, and the red is the buffering ratio. So you see that the buffering ratio is actually going down as there are more users watching the stream, which is usually a bit the contrary when it's only a CDN, I mean, it's only a CDN distribution. I'm getting to the end of the presentation. I just wanted to show you what happened a few weeks ago as you guys won the Women's World Cup in France. This is some of the numbers we've seen during the competition. You see that basically the blue part is the CDN offload, so what's been transiting through the peer-to-peer, and the pink part is coming from the CDN. In that use case, we only have the peer-to-peer activated and not the multi-CDN switching, so it was only one CDN and peer-to-peer network. But that's kind of show you a little bit what's the screenshot from the dashboard that I made, and the kind of traffic that can be handled, especially during the spike time, by this kind of approach. Thank you very much. That's all I got for you guys.
Thank you. Are there any questions in the audience?
So my question would be, in the OTT space, a lot of people are using connected devices, right? And basically, are you going to be trying to intelligently tier to use them more as a CDN because they don't turn them off, right? And so also support for something like a Roku?
So could you repeat the beginning of the question? The second part, I got it, but the beginning?
Basically, OTT devices being treated more, basically as the actual senders more than they would the receivers, right?
Yeah. So, I mean, I think it's going further than that. Is the OTT device is treated as a piece of the CDN architecture to make decision. So it can be a senders, or it can be a smart switcher. It can be where you can measure things and switch directly by looking at what's going on the device. And going, following your second questions, this kind of technology are now broadly supported. One of the devices that is still not supported by most of the vendors is Roku indeed. It's not a technical barrier. It's just that Roku is pretty closed environment today. So if there's anyone from Roku in the room, I'd love to talk to him. But yeah, that's more like a political constraint than a technical constraint.
So if I understand correctly, your client software basically switches between different CDNs and also peer-to-peer. For the cases that, say, the manifest already has a list of multiple base URLs, multiple CDNs, what do you do there? Because then the client, the streaming client itself, can also switch between different CDNs.
So two things. For the peer-to-peer, if we have, we can use a different ID that just the URL to make sure that it's the same content. So it's encoded the same way. We can do peer-to-peer even though you have different URL for different CDN, and we can do exchanging of segments between these different sources. That's not a problem because you can use the URL of the stream as an ID for the content, but you can use something else. The second question about CDN load balancing, for this one, you need to have the same origin. Because if it's not exactly the same stream, you're going to have a hard time switching between the different sources. We're working on some optimization right now, but if you have the same origin and then different, or like a shield before and then a different CDN, this is the best use case to use our solution.
Okay, we have time for one last question.
So I am curious about the clients that are doing some proxy or VPN and getting a different network location, seemingly. So in that case, do you still, I mean, how do you actually measure that a peer is close to another peer or not? If, you know, a lot of people are still doing proxying or VPNing to another location to get certain content, right? So.
Well, there's, so that's a broad question about how we make sure that users are close to each other. So you have the generic behavior of the solution, who's taking into account a bunch of parameters, some database of IP to match them in the best way possible. But then you can implement some additional rules for the matching. And one really good example when you're talking about VPN is that we got a lot of experience of behind the firewall streaming, where in that case you need to be very careful on the way you are matching the peers together, especially if there's like VPN or if there's different sites. So if you have people in one site that you don't want to do peer-to-peer with another site. So in that case, you can implement some specific rules, or you can implement ISP rules, for example, or ASN rules to make sure that, for example, for ISP1, you want to activate the technology, but not for ISP2. So you can add additional, we added a bunch of controls that you can put it in the system that is on the top of the generic behavior that might not be able to see some of the things you just said.
Thank you. And another round of applause. And